Welcome to the final week of the AI Summer for 2024. We're going to be talking about some really exciting things today. But what I'd like to do first is I'd like to harken back all the way to the beginning of the entire AI Summer at the beginning of May. Just remind you of where we were, and then to talk about ask you some questions about how you think the models are able to do what they're able to do. So you might recall that one of the very first things that I showed was this demonstration of a talk that I went to. So you might recall I went to this talk. It was an organic chemist that was speaking, and this was in the chemistry department, the colloquium. This was not a talk for me, actually. But this person, this researcher, did work with data science applied to organic chemistry. And so to keep up and to understand what was going, what I did was I used what at the time was GPT-4V. And I would take pictures of the slide, and then I would ask questions about what was happening in the slide, asked it of GPT-4V, and it actually did a really decent job, not just of sort of telling me that it was a slide, but getting after the text that was in here, getting at all the different elements that were in here as well, recognizing, for example, that it was talking about chemistry, and it told me what DFT was and described the role that quantum mechanics was playing in here as well. And, did an excellent overview. And a couple of things you notice here is, it's obviously going to be image. The text is at an angle, and it's really a kind of oblique. It's not all that clear, and yet it was able to do all those and even do things like pick out this regression model right here and tell me what the different parts were that were part of it. So pretty astounding, its capabilities. And since then, we've had the release of GPT-4o, which is an even more capable model. Even more exciting than that is that on May 10th, a new version of an open source, completely open source model that is also multimodal was released. It was an update of something that was called Lava, which is as performant, if not a little bit better, than GPT-4V, this one that we were doing here. It's not compared yet to GPT-4o, but still something that created with far less compute than GPT-4V was, far less compute, and yet had similar capabilities. This is astounding that so quickly we have gone from just 6 months ago, where really these were not very good. The multimodal models were not great, and they would also hallucinate significantly about what was actually in an image. It would get it approximately right, and then it would generate details. All the way to today, where, okay, we have OpenAI creating a really nice solution, GPT-4V, and now GPT-4o, which is eminently usable. But now, on top of that, having an open source version of the model, which is far smaller, faster, and trained much more inexpensively. How on earth did we get here so quickly? So let's go and pop forward a little bit. So let me remind you about the architecture that we've talked about. Yeah, okay, come on past. All right, I'm going to have to pull this in here. So you'll recall that we sort of had this as an overview. I just want to remind you about this and about the different parts here. So you recall that whenever we talked about a large language model, that what's happening is that we're putting in context, and and then we have token encoding. Can somebody tell me what is happening in the token encoding? Can somebody tell me what that is? And I can't see I can't see your images right now. So if you could raise your hand or put it in chat. Okay, so Mohsin, what do you think? And then Harper, I'm going to ask you.
You're creating, I guess if it's a sequence, like a context, you're assigning subwords to
Yes,
numbers.
that's it. That's right. So we're assigning tokens to words or subwords. Excellent. That's exactly right. Because remember, any deep learning model can only deal with numbers. It can't deal directly with words the way that they're set up right now. So yeah, so token encoding is taking the word or subwords, usually subwords, and turning them into giving them an index number, right? So these are going to be integers. Um, and let's see. Oh, now I don't remember who else was raising. Harper, I think. Harper, do you want to take a stab at token embeds? What's happening with token embeds? And you can pass if you want to, but you had your hand up before, so. And
It uses so token embedding uses a high dimensional semantic space to calculate vectors between each token.
very, yes, you're jumping ahead a little bit, but yeah, the high dimensional space is important, right? So what's happening here is it takes each of the tokens and gives it its initial position in this high dimensional space. Oh, so we had the word cat. It was 42. I'm going to do just a lookup into this vector. So it's like a lookup table. Oh, here's the vector for 42, the starting place for it, right? Yes, and so this is actually the initial placement of each of these individual tokens and their embeddings, each of the individual tokens into this high dimensional space. It's the embeddings. The embeddings is a long vector, and the vector is exactly the length of this high dimensional space. Dimensionality gives it its location. So it's a vector. You can think of it like a point location in this high dimensional space. Fantastic. Okay, so at this point, we're doing embeddings all the way until we get to the very end. So we take the embeddings and we feed it into the decoder stack. Can somebody tell me what are the two parts of a decoder stack? Remember, there are two parts to it. Sometimes more, but there are usually at least two parts. Can somebody name one of the two parts in the decoder stack? Let me go ahead and I'm going to call out to folks,
It's
and you
a
can pass.
feed-forward network.
Fantastic. Yes, that's right. Feed-forward network. That's the second part. Excellent. All right. What's the part that comes before the feed-forward network?
Attention.
Fantastic. That's it. Attention and then feed-forward network. Sometimes there are multiple layers of attention depending on, what kind of architecture you're dealing with. But for a decoder, it's going to be an attention and then feed-forward. Fantastic. So if we sort of dive in to one of these a little bit, sort of explode out what's happening here. Yeah, we have multi-headed self-attention. These are the different embeddings going in, and then these are the different embeddings coming out. So you recall the multi-head attention allows the tokens to be informed by one another. So if cat is there, and if you have tabby someplace else, then that cat's going to mean like a domesticated house cat, right? So this is averaging, a weighted average across all the tokens. So each token gets informed by all the other tokens. Remember, that's kind of an expensive thing to do. This is where a lot of the compute goes. But that's what happens with that. And then once each of those tokens is now informed by the other ones, now it moves into feed forward, and each of those tokens is further enriched. So let's say that cat now means a little bit more like domesticated cat. So now that token embedding is to be enriched with other things having to do with domesticated cats, like Maybe there's the sense of litter box, or maybe there's the sense of allergy, for those that are allergic to cats. It could be all those things that inform that embedding. And then that gets fed into the next stack, and the next stack, and the next. So this is all a process of each of the tokens informing one another and then being individually enriched until we get to the end. What happens, and it's not here, but what happens at the very end? I'll go and I'll put this up. What happens at the very end? I call it next word prediction, but that's not quite it. What's really happening at the very end of a decoder transformer, this generative AI transformer?
Tokens are converted back into language
Almost, right? So you
or back into words or no. Oh,
that's very close, right? But we got to do something even before that, right? So first we have to figure out, so we have the embedding, and you're right, now we have to get it back into a token. So we have to have the unencoding, but even so, as part of that though, is there just one token that this vector goes to?
No.
No, right? It's close. It's close to a bunch of them. So what we do is we give a probability distribution over all the possible next tokens. So we take all the tokens, because we have a dictionary. We can enumerate all the tokens that we have. And what we do is we assign a probability to each one of those tokens saying which one it is most likely. Because really, you have tokens that you can think of, like the prototypical token for unencoding for cat may be right here. So how close is it? Well, it's not too far away. But there might be another token which is even closer. So another embedding which is even closer. So what you're doing is you're giving a probability distribution over the set of all tokens. So that's what's happening. And then we can either choose the most likely one. We might add a little bit of noise in there. And so we have a little bit more creativity. But then what happens is then we choose a token and then we generate the next token. And then we wrap around. So that's exactly what is happening here. This is called auto-regressive. You choose a token, you put that back into the context, and then you rerun everything. So,
Jesse, when
yes,
you say auto-regression, can you
yes,
explain that terms versus what Miranda talked about back propagation last 2 weeks?
sure.
So
No,
because
that's a
my way, I
great.
was like, back propagation is like going back to the parameters to see what is wrong in the system.
Ooh, I like your thinking about that. And mathematically, what's happening is with backprop. Well, first of all, let's separate out inferencing and training. So here we're only talking about inferencing. So we're using this. This is like you're typing in and you're getting responses out. This is the model running and actually giving you text back in response. No training taking place, no learning taking place in terms of the weights being changed, nothing like that. It's taken exactly what's already been trained and just using that model to generate. We call that auto-regressive. We call generative AI models auto-regressive to differentiate them from other types of transformer models that might be doing something else. Because very specifically what happens is we take this last word right here, say board, and then we put it back in here, ships at a distance, everyone's wish on board. Great. Generate the next one. Now the next one. So generative AI can keep on generating these words, and the word which is chosen for the next word informs what comes next. That's why it's so important. When you saw the last week, you saw the tuning by proxy, where you saw that you can add the probabilities and actually steer this by saying, oh no, go down this path, not this other path. And then it continues down the path. That's called an auto-regressive process. So that's just inferencing. Now let's talk about training. With training, we're actually explicitly saying, hey, guess the next word. And if the word that you chose is not right, then go back here and explicitly change these weights. This is called backpropagation, very expensive to do. And what it will do is adjust any of the free parameters that you have here. And so the model can do better more and more. This is the model learning. Extremely expensive. Some model learning. You can train it in new concepts, new tasks, new ways of doing things. But this is when the model can learn new things and new tricks. And that's called backpropagation. Does that answer your question, Sim?
Yes, thank you. It's very clear.
Excellent. Very good. And we had another hand raised that I saw kind of go away. What was the question? Yes.
My question was, how does the large language model know when to stop? Like, is there a stop token?
So there can be a couple of things. One, you can say, generate the next 20 tokens, right? That's sort of outside. So the model itself doesn't know, it's using a rule. So this has to be outside of the model. The model's always going to generate that next probability. So let's say that you have outside you're watching, and if it generates a stop, and yes, there are stop tokens, depending on which tokenization scheme you have, you could stop. Or if it reaches a period, you could stop. Or if it gets to the nth token, and you said generate n tokens, then it'll stop at the nth. The model itself doesn't know to stop. It's simply, you are asking it to rerun and generate the next token. You can ask it to generate the next token or not. All right. So here's a big question. We're going to do breakout rooms in just a moment. We're going to do 10 minutes of breakout rooms. This is all well and good. Very useful. We've known this. We can write computer programs with this. We can, if we have long context models, we can put whole papers in there and reason against those papers. Tremendously useful. How do you do this? How do you do images and text together? So think about all the different ways that, all the different things that we just talked about, right? How this works. Tokens goes into embeddings. You do things with the embeddings, and then you can generate words. How do you do a multimodal model? Okay. So what I want you to do is go into your rooms, and let's go ahead and give you the link to the document here. So I'm going to ask you to go ahead and I'll put this into chat. Here's the link to the breakout document. We're going to go in there in just a moment. What I'd like for you to do is, and remember, when you go into the breakout rooms, good way to do it is turn on your camera, unmute yourself, and have a conversation. Somebody take down notes of ways that you might want, if you could design it, how you might make a multimodal model rather than just a text-only model. So Charo, would you mind, before we go into rooms, you all understand? Any questions before we jump into the rooms for 10 minutes to do some brainstorming? All right, let's go and open up the rooms. We'll see you in 10 minutes. All right. By the way, I did a deep dive into Lava Next. My God. It's impressive.
It's really
There are so many things coming out.
I know.
That is so cool.
Lava Next. So, and you'll see, I mean, they took the frozen part and just used more and more advanced large language models with it, including instruction fine-tune, plus they did tool training on it. And so now they have a model which is equivalent to or bests GPT-4V, plus has more tools. So you can say, hey, in the following image, segment out any children. And GPT-4V cannot do that. I mean, it's just like, anyway. And if anybody's not writing anything, we might want to pop it in one of those rooms. You can see people getting into them, but they're not. Don't see any ideas yet.
probably take a little bit. I find
Exactly,
people
it's a
are
big
usually,
ask.
yeah.
Anybody want to go into room 5? There are only 2 people in there. They don't seem to be speaking.
Yeah, I think people left that room, it looks like, somehow and went into different rooms.
Yeah. Oh,
Maybe
yeah. 4 emptied completely. 5, I'm showing just 2. Or is it fully empty now too?
I
It looks like the geode one now has people from other
Okay.
oh yeah,
places.
they're like usually always in office hours together. So I was like, let me put these office hours people
Oh,
together.
okay.
Oh, nice.
Oh, yeah, okay, yeah, these people, okay.
Yeah.
Is Abby who's in room 5? Is she not part of Translate? She maybe just didn't prepend her name.
Oh,
But she is.
okay. Should I just move her in that room?
I might pop in and say, hey, you want to join? Or
Okay,
up to you.
I can just go in that room right quick. Oh,
They're
that's
talking. That's good.
just kidding. Maybe I can't go in there.
Are y'all co-hosts? Make host. Yeah. Yep, y'all are co-hosts.
Oh, there we go. Sorry. All right, I'll be back, maybe.
Oh, and I met Declan, Matthew, and Jake, who are our first fellows. Hello, Zingbo. Did you need to be helped back into a room, or are you just joining us? Hello, Kevin. Folks are in breakout rooms, and they're going to be there for about the next 4 minutes. I challenged people to come up with a way to make a multimodal model, one that could do images and text, just brainstorming. Would you like to be thrown into a room, or would you like to hang out here with us?
Sorry, I had my speaker on mute. Just got back from dropping off kids at camp.
Okay, yeah, that's fine. So we have breakout rooms. We have about
Yep.
another 3 minutes. And the ask is to brainstorm about how you might create a multimodal model, given what you know about text transformers. Would you like to be dropped into a room, or you want to hang out here with us?
I'll check out a room, see what people are talking about.
Okay, great. Shara, I'll let you take the honors if that's all right. I'm good, getting some ideas here. Okay. Mhm. I'm gonna leave it open because people are typing now, so I'm gonna. Hey there, Abby. Welcome back, folks. We have a few folks writing down some notes now, so we're gonna let them get finished typing up their notes. Hmm. All right. All right, I'm gonna close the rest of the rooms now. Welcome back, folks. All right. this was a big ask, but you all actually have some nice ideas here. So room one, this is DSSG, DSI. Can somebody share some of the ideas that you had in that room, room one?
Hi, my name is Sim. I'm part of the room one. So some of the idea we were talking about the pictures.
Mhm.
How do we break them down? We all learn about words and other stuff. So we are thinking about breaking down into numerical, like ones and zero, so that in the semantic space, we can find the average, to find the attention to get to the image. But another way Harper brought up a good points that how can we train the system is by uploading more pictures to the system to like let it learn and figure that one out. And he also mentioned about in order to make sure all these pictures and interpretation was correct, it went back to what we just talked about to do the back propagation to like, hey, can we catch things correctly? So we are kind of like touch base about context learning and then prompt engineering in about that one. We did mention a little bit about LangChain, but we have not get into detail how we can do that part.
Okay, okay, good. So you're realizing that you need to figure out how to get an embedding out of that image in some way, get an embedding, and then you've got to figure out how to develop context sort of between the two. That's great. So along those lines, just to mention a little bit about how you can get an embedding from the model, and we can pop this up here. Just will remind you that this doesn't have to be text. We do have things called vision transformers that actually work with images and produce embeddings. But it's not word and images, it's just images. So we have vision transformers and other things that are more advanced from vision transformers, like something called Q-former. All right, so now we get the sense we have these building blocks. I like that a lot. Room 5, can you give a sort of a high level summary of what you're thinking here? You don't have to get all into the training, but sort of high level what you're thinking here in room 5.
I'm gonna go ahead and pass on that. Yeah.
Oh yeah, yeah, oh yeah. You don't have to, yeah, Abby. Thank you though for were you the one who took down the notes?
Yes.
Oh,
Yes.
you were
Yes.
so
Was that
good.
none of?
That was great
Oh
note
no.
taking. But yeah, no, you don't
Oh,
need to.
hold on.
Somebody else from
No,
room 5.
none of that was
Abby's
me.
already done her work.
No, no, no. None of that was me. My partner, their mic does not work, so that was all of them.
Oh,
That
okay,
wrote
got
that.
it. Okay, I understand. So let me pick out a few things here then. Y'all did great work for not having a non-working mic. Congratulations. So the idea here is integrating both models. In this case, it's an image recognition and word recognition into a unified application. I like this idea. So take something which is an image model and something which is a text model, and then combine them together in some way. So, all right, that's a solid idea. Now let's go ahead and let's see, room 6. Can you give me a high level idea of what you were thinking here?
Yeah, sure. So I was thinking, and I guess the rest of my group as well, we're talking about how we could potentially use dynamic weighting. So instead of um setting weights and then just using those weights as the activations, instead use uh like a dynamically adjustable
Mhm.
weighting system. And then alternately, or I guess in addition to that, we talked about ensemble models that could extend to using a sort of feed forward method to reach a certain confidence threshold until that specified confidence level is met. And then
Right.
lastly, you could use like a hierarchy of
Mhm.
transformers where you have certain low-level transformers just handle like pixels and words, while more sophisticated transformers could handle the more complex or
Excellent.
abstract concepts. And then lastly, and this we didn't fully flesh out, but we thought about taking an image, converting it to text, and then adding that text back into the input for handling the rest of the text.
Okay.
And potentially, I was watching this video about how you could take a picture a neural network in 3 dimensions and then sort of save on certain features being learned multiple
Yeah.
times by
Yes.
so potentially this way you would eliminate for that sort of redundancy.
Great. So you all, there's one additional thing I'm going to add here, but really you all have sort of intuitively covered really the space of development over about the last 8 months that has gotten us to where we are right now. So that is great, some great brainstorming. The one additional thing that I would add is maybe what you do is you create a model, and so you tokenize text and images. So a single huge token dictionary where you can tokenize images and you tokenize text and you have it learn on all of that together, which is yet another way. Fantastic. What I'm going to do is I'm going to take you on a tour right now of a number, like almost 10 different papers. So we're just going to go all the way through, but I'm going to organize this in a way, kind of along the ways that you were just thinking. So what we're going to do is we're going to first think about that first general problem of trying to come up with a model that can combine images and text. We're not even talking about generating right now. All we want is to have a model that creates embeddings for images, like Vision Transformer, creates embeddings for images, but then also puts this into sort of a common space where there are also embeddings for text. This is called CLIP. Think of CLIP not as being a solution, but rather CLIP as being one of the building blocks that you use to actually solve this problem. So what CLIP does is it takes text and then it takes images and it encodes them into a common space. And it uses something that's called contrastive learning. And the idea is that if you give text and an image that belong together, so in this case, Pepper the Aussie pug. Okay, is that a pug? That's not quite a pug. Oh, Aussie pup. There we go. Pepper the Aussie pup. That goes together. These representations ought to be close. Whereas if I said a cute penguin on ice, then you want these representations to be far away. So the idea is contrastive learning. Things that belong together should be represented close together. Things that are not similar should be represented far away. Man, and that's like, if you get the sense that that's not a very rich way of learning, you're right. That means that you have to have millions, billions, trillions of tokens to train on. So this is a cool method, but you're going to need to have a huge amount of compute to be able to do this, to have it come up with something which is useful just based on the training alone. So a ton of training data, contrastive learning, but now you have something which is like a general purpose thing. How might you use it? Well, you can use it to generate some text or to label or you can use it for lots of different things. It's not going to tell you about the picture. This is simply going to give you basic captioning kind of information, and that's it. But it's an extremely useful first step because this is one building block that is images and text in the same space, and that's a good first step. Okay, now let's go a little bit more beyond this because we can't do much with this. This is a building block. You can't, it's hard to build it on top. It's hard to train this to do more things. You can't really train it to do question answering. You can't train it to give you, you know, to do things with the images. Not going to happen. So let's go and talk about another. This is called FLAVA. So it's called FLAVA, Foundational Language and Vision Model here. And this is interesting in that it uses, for training, it uses masking. So here it takes images and it does an encoding of this. It learns about this by doing masking. But here's the idea. Some of you all mentioned like ensemble. This is exactly what this is. So this is an ensemble where you have an image encoder, you have a text encoder, and then you have a multimodal encoder that takes both. And think of this as like a general purpose framework. You can train it to do additional tasks on just the vision, or just on the NLP, or on both. So this is one of the earliest, you know, this is an early example where these things can be, you can use this to solve problems. You just have to come up with custom heads on top of this. So this is not something that you can just ask to do things. This is not something where you can say, describe any vehicles in the picture. Not going to happen. Instead, what you can do is you can train specific heads to do things for you with images and with text. So you'll notice this isn't tied together all that much. And the trick here is that you're training with masking across all of these all at once. And it's the training which is holding them together. So they learn in concert by doing masking of the words or masking of the text or both. And then you give it a particular task to do. And this can be complete the image, complete the text. So that's kind of an earlier example. Now, remember that the one that I added in was it actually here? Let me, before I pop in, I don't want to go past too fast. What questions do you have about this? FLAVA is it's not one of the leading models which is used, but it's an important one to note. Any questions about FLAVA?
I am actually lost on the multimodal encoder part.
Oh,
Because let's see if I get the image and I get the wording, and what prompt the multimodal to create the encoder itself. Like I'm missing the link. Like, hey, what prompt and initiate and trigger that multimodal encoder?
so here, what's happening is that you're actually combining all of these together into a single, right? And so you have a single encoder which will do the encoding of both. So think of this, first of all, ensemble. These are a bunch of methods put together. Second, this does have the idea of actually combining all these these tokenizations, this encoding into a single encoding space, which is then used by the task heads. We're going to get more specific into what's happening in some simpler to understand examples in just a moment. But here the idea is that the encoding all is into a same space. The take-home message with FLAVA is you have these different task heads, some which are trained on encodings of both, some which are trained on only one or the other. And then very similar to what you all were saying is you might choose one versus the other depending on the task. And I realize it did not answer your question very well, but we're going to get into more detail in just one moment.
Jesse, what would you said the first one for contrastive learning, the problems with it were that it takes a ton of data to train and also, and also a ton of compute. What's
Yes.
what's the pro? I mean, and you mentioned the pros of
Yeah.
FLAVA over this one, but what were the shortcomings of FLAVA that
Actually,
required
what'll
the next
happen,
level?
yeah, so think of these as solving two different problems. So CLIP is actually like a foundational idea. So you can actually, now you can build other things on top of CLIP. So if you want to, you can take the idea that some of you had of turning the image into some text and then putting that into the large language model. You could do that using Clip. Just give like a quick caption of what's in there. And so think of Clip as one of the building blocks that you could use. You're going to see in just a moment that there are some solutions that actually use Clip as part of their solution. Just one of the building blocks, because one thing that you can get out of here is you can get a useful representation. You could do this image encoding and get the embedding out of it. So this is a way to get a useful embedding that's more text-like out of an image. So if you want to get an embedding that is text-like, so an embedding which might work really well in its semantic space, maybe you run it through Clip first, and then you sort of do an ensemble with something else. Look what's happening here. Here you have an input image and you have an image encoder. So you're not going to use it here, but you could use something like Clip right here, or you could use Qform, or you could use something like that just to get that embedding out of this. Text, you can use whatever large language model you want to have. The idea here is, though, that you have these multiple models, they're all getting trained. So you might have a starting point, but they're all getting trained. So it's not really Clip versus this other one. This is kind of like the first crack at the idea of multiple models working together to solve that multimodal problem. That's what Flava does. So Clip, just starting point, building block. Flava, first pass at this, multiple models working together. But let's move this on. What about a model that's a single model, but instead has multiple tokens? So maybe what you do is you have a big tokenization scheme that can tokenize images and words. Well, that's what Chameleon is. Chameleon's a newer model, but this idea has been around for a little bit. And that is, hey, some of your tokens represent images, some of your tokens tokenize words. So now for your tokenization scheme, you have words or subwords, and you have picture parts. And picture parts often being just a square, that's Vision Transformer just used a square subset, and each one of those was actually called its own token. But you can also use more advanced versions of tokenization schemes for images as well. But the idea here is this solution is just not very far from this at all, right? It's just that this tokenization scheme now covers both images and text. So everything else stays the same. Now you're just tokenizing image, text, whatever you have, and you're doing everything and you're generating text. So that is Chameleon. Again, Chameleon, huge amount of text. The nice thing is you can interleave text and images. Here's an image. This is a bowl of fruit. But what's missing from this is protein. And then you might have a picture of a protein bar. You can add the protein bar, so you can have interleaved images and text in a single narrative, and this model can handle it. It's an autoregressive mixed modal model that has tokens for images and text. Significant training. We're talking about 10 trillion tokens to train Chameleon. And this is, again, you've got to be Microsoft, you've got to be Google, you've got to be one of these huge places with tons of compute to train this, but they did it, and they have it. So we've gone from, so far, multiple models working together to try to solve a problem, to a single model, but that has many different types of tokens. Questions so far about the first two types of solutions that we've covered so far? Okay, then let's talk about sort of the next step. We have spent a lot of money training models like Clip, models like Llama that do text. Why do we want to necessarily throw all that away and have to retrain something? Why can't we use clip and another large language model as building blocks. Well, that is what the Flamingo model architecture is. So here's the idea. You have a vision encoder, you have vision encoders, and you have text encoders. So think of this as being, could be clip, could be another something which is doing encoding of the images. And then here you have text, and you have text and images interleaved here. So these are frozen. That text model is frozen. The vision model is frozen. They are each unimodal. But what happens is you take the embeddings that come out of those and you put those into a trainable model. This is very, very close to, was it room? Let's see, which room was it? This was room 6 that had this idea of like averaging. When you say averaging, you're talking about transformers, you should be thinking attention. So what's happening here is that you're using attention to average between the embeddings that are created by the vision encoders and the embeddings that are created by the text encoders. So I think of this as being late binding. Representation from one space, representation embedding from another space. You let a higher level attention model, transformer model, a specialized transformer model, handle both of those and learn on both of those. So you train the model on these frozen models. This works pretty well. The nice thing about this is you don't have to retrain a whole vision model. You don't have to retrain a whole language model. Instead, you only have to train this part right here. You train the blue stuff from scratch. This architecture, a little bit complex, tough to, so the downside is that this still a fair amount of training that goes into this. Also, while it's very useful and can do lots of different things, it can be difficult to get this to take on brand new types of tasks. The nice thing is that this works much more like a large language model. You can do in-context learning. You can do zero-shot things with it. So it's useful for that. It's just, it's fairly intensive to train even though you're leaving a lot frozen. But man, we're getting a lot closer. But the idea is take embeddings from two totally different models, have another model learn on the two embeddings. Questions about Flamingo? All right. Let's do something stupid. So the whole idea here is that we've wanted to take the embeddings from the images. So we start with the images, we want to get embeddings somehow, and then we want to put that in the same space, in a common space, with embeddings from words. And then once you have the embeddings in the same space, then what you can do is you can generate text off of this and answer questions. And you have a lot of flexibility if you have a nice big large language model. So you can ask questions about the images. You can do things like that, but they have to share an embedding. If you get a summary of what's in the image and you just feed that text into a large language model, you lose all the information that you have about that image. But if the embeddings are there in the same, then one can influence the other. So for example, let's take this picture right here. It might say cat. And then you might put that into a large language model. Well, that's nothing. But if you put the embedding in there, then the meaning of cat, posed, is that a tabby? I don't know if that's a tabby, but multicolored, all those concepts would be in the embedding if you were to use like a clip embedding or something like that. And if that could be in the same space as the words, now you're cooking. Now you can ask questions about it. Now it can more deeply inform the text that's generated. Let's think about the stupidest way to do this. One stupid, brilliantly stupid way of doing this is, all right, take an image. Here's a drawing. you use a vision transformer or something like Q-former. These are vision transformers. These are a way of capturing and embedding the images into this embedding space. So we're not using, so we're kind of going directly here. And you have a linear layer. This is simply to create a projection. So remember, all of these are this right here results in an embedding. And remember, an embedding is a point in a high dimensional space. It's you can think of it as a vector. And the linear layer says, okay, project this down into the same space as a model which does text. So Vicuna is a model which is text only. And what you're doing is you're kind of abusing it. You're like projecting down into this space directly. So what you're using is you're just borrowing the embedding space from the text model. So think about this. It was not built for images, right? But you're projecting directly down into it. But let me ask you about this. Give me a thumbs up if you would. Okay, I want to be able to see your face. Give me a thumbs up. Do you think that you could describe an image? If I give you a photograph, could you put it into words and describe what that image was? Yeah, yeah. So it's absolutely right. So that means that your embedding space for your words can describe visual scenes directly. So the idea here is, well, why not just learn a projection directly from whatever visual embedding you have that's pure vision and project that directly into this high dimensional space? You don't have a common space between the two. You're borrowing the space from the LLM. Okay. So before I move on, questions about that. We're going to talk more about it, but questions about that. So you see what's happening is I'm in a totally different space. I got the embedding for an image, and I'm projecting it down solely into this large language model's embedding space.
It seems like that would be very inefficient. Like if you think of the adage, picture's worth 1,000 words, you're going to need a large prompt to describe that picture.
Right. If you were to try to do this using words, and remember that was one of the earlier versions, right? Try to use words, but this is, you're projecting directly into the space, right? So it's not words. It is the semantic space. So is there a space, a part of the semantic space, which represents a grassy lawn that has bald patches?
Oh, maybe, yeah.
Right. It depends on the model, right? So that's what's one of our first things. If you have a crummy large language model that's tiny, then maybe not so good. But if you have a large model that's very rich and well trained, that projection would probably work better. It turns out this is exactly the case. So when this was first tried, and this was what I was just showing you, is called Mini GPT-4. I was so excited when I saw this, but it did not work very well, frankly. Mini GPT, it was okay. It was cool that it was able to do things, and it would get things right. We tried this early on. Abby, I don't know if you remember, but very early on, we did some early experiments with trying to do picture books with Ada. And it would like come up with some descriptions, but then it would make up a bunch of things and it would miss details. Well, it turns out that really what the problem was not the idea, but the richness of the model and how it was trained. So along comes in May, this was updated in May 2024, but this actually came out in November 2023. This idea of taking a vision encoder, and they used CLIP. They used a decent sized version of CLIP. And what they did was they added a multi-layer perceptron. So not just a direct linear but instead a learnable multi-layer perceptron that would then translate this into that same large language model space. So words, you do the same way. What is unusual about this image? Usual in tokenization and embedding, that happens the same way we were just talking about. And then you have an image which is projected into that space, but in a learned mapping. And it turns out this works really astoundingly well. So in this case, you know, is this unusual? Please explain in detail. So it's actually able to answer questions like this. So what is the color of the shirt that the man is wearing? The man is wearing a yellow shirt. What is the color of the shirt? Let's see, you know, so it's able to answer questions off this. Why? Because Vicuna, the language model itself, can answer questions, and because the embedding is directly in there, it has access to everything. So if you're asking about the person or what's funny or what's unusual, it has access to the rich information in the image. So actually, it turned out that this worked really pretty well. So the next advancement is, rather than dealing with just that whole image, split it up in two different ways. Do small splits and do a resize, and so you can encode both the entire image and the local information. And those both get sent into the LLM. So how well does this work? Well, okay, well, so let's see if we can get to the, so this is lava right here. And then these are, let's see, do we have, I might have to, so it's out for, so the bold is the lava models, and it is pretty much outperforming everything else, every other model which is available to do, open source model, which is able to do this kind of work. And it can do things like, let's go and take this. So here's this image right here. We're going to zoom into this. Maybe we're going to zoom into it. Yeah, here we go. So use it. If there are factual errors, the question pointed out. If not, proceed answering the question. What's happening in the desert? So this is saying, what's happening in the desert? GPT-4V says, I'm sorry, can I answer the question? As there's no context about which desert you're referring to. What does Llama 1.5 say? There are no deserts in the image. The image features a beach with palm trees, a city skyline, and a large body of water. Are there palm trees? There might be. So check out GPT-4V, the biggest model trained by OpenAI, not being able to do too much. Lava 1.5 being able to actually do this. Take another example. Please read the text in this image and return information in a JSON format. So this is it, kind of crummy. GPT-4 does okay, makes a few mistakes. Lava 1.5 actually gets most of that information right. So this is a model which is trained on far less compute. As a matter of fact, 1.5 was trained on a single DGX. GPT-4V probably on thousands of DGXs. So the fact that it's competitive is astounding. And really, where the power comes from is this very simple, brilliant, stupid idea of projecting directly into the space of the large language model. Why? Because large language models already have beautiful embedding spaces. So let's leverage them. And don't try to make your own embedding space, which is separate for the images. Borrow that very nice, rich representational space that's already been learned by large language models. Let me pause here. Observations or questions? Shoot.
Okay, I have a question for mapping the image to the LM space. So does the image usually takes a larger space than text, because one image can contain much more information than a single text.
Yes. Yeah, absolutely. So one thing is it's really helpful to have longer attention, right? Note this trick that they just added just this month in something that they're calling Plus. So they're calling the new model Lava Plus. And the idea is that you downsample this. And so this might be a big image, a really big image. So one thing is you split it up into the smaller parts and you get the embeddings for each of the small parts. But in order to not lose sort of the larger context, you also resize that image, and so it can fit into a single encoding, a simpler encoding. So this way you get the fine detail by doing the embeddings for each of the small images that make up the larger image, and you also resize to get the larger global context. So maybe right here, in this one, you can't see that he's sitting weirdly on the back of a taxi, ironing something is what it looks like. But in here, you get the whole context of, wow, he's standing on the back of a taxi. All right. So yes, you need long attention because yes, it can take up a lot of space to do that. But once you get it into that embedding space, then you're good to go. Does that answer your question?
Yeah, and I have a follow-up question. So suppose we have the embedding of an image in the LM space.
Yes.
Would we be able to transform the embedding back to the original image or another image with low quality?
So to transform it directly back into the image, you would have to have something like Chameleon, right? Because what Chameleon has is it has tokens that are both for images and for text. In this case, with the LLM doesn't have tokens for images. So no, we can't do this trick here where this Chameleon, because it has the tokenization, which covers both words and text, where it can just directly generate a new image. Can't do that. But so you tell me, if you wanted to make an image right now, you could describe an image, like describe a scene. What would you do to generate a photographic style image of that description?
What would I do if I want to generate a photographic style image?
Yeah. Is there any sort of tool that you know about that might be able to do that for you? A young man walking in a field in heavy rain with big trees. Do I hire an artist?
Okay, so simply give a description.
Yeah.
Yeah.
So go ahead and put this in chat. Yeah, so yeah, Umang, Stable Diffusion, that's it, right? We know these tools, right? We can give the text prompts and then Stable Diffusion can generate those images. So what if we wanted to do those kinds of things, instead of just using a Vicuna model, what if we used a model that knew how to use tools? So what if we used a model that could actually call Stable Diffusion or call another model and say, make me an image of? Well, it turns out that is exactly what the next step was. And this was, and this is November 2023. This when they first started to work on the Lava Plus. So the idea here is you absolutely take Lava, but what you do instead is you use a richer representation, a richer, let's see if they, yeah. So what you do is use a better model. So back here, where we're using Vicuna, which is okay. But what if you used a really great LLM, an LLM that knew how to use tools? And so, the tool could say, so in this case here, we'll zoom in a bit so you can see this. So you might be able to say, for example, you might be able to ask for it to, just describe what's in the image, but then you could ask it to, if it knew how to write and ask for a tool use, you could ask for it to do object segmentation, semantic segmentation. You can ask it to do box segmentation. So you can actually ask it to do different things, so long as whatever language model you were using knew how to use the tools. And so what does this look like? So you kind of put it in a loop. So what you do is you give it some instruction, and it's more like an agent. And so the model actually makes a call to a tool, uses the tool, puts that image back in, right? And then until it can come up with a response. So this is a model that knows how to use tools. And the trick here is you don't have to improve any of this. What you've got to do is have a better and better model that you're doing the embeddings in. And it turns out to be a huge way to advance the capabilities of the models. How advanced? We're going to see that in a moment. Let's go and take a 5-minute break, and we're going to come back, start thinking about all the different advancements that we've had in large language models and how much of a difference that could make in this kind of multimodal model. And I want you to think about how well you think that this new kind of an approach might stack up against GPT-4V and GPT-4o. Let's go and start back up at 10:19, okay? Or 19 minutes past the hour. Sound good? Okay, we'll take 5-minute break. See you back at 19 past. All right, welcome back, folks. So we're working with this idea that maybe a really good approach to dealing with multimodal models is, instead of having an ensemble of models, which requires a lot of training and coordination, either from training from scratch or something like Flamingo, where you have the frozen models. Maybe what we do is we just use that representational space, that embedding space of the large language model itself. So what would be some ways that you might improve this model, keeping just that same architectures? What are some ways that you could improve the capabilities of this model, make it work better, or give it new kinds of capabilities? What's one way that you can just improve any model? Yep, Anand, exactly. You can train it more. So that's one way. So you can train it more on more data. You can also train it on new tasks, right? So maybe one thing is we can train it how to do different things. Because remember, one of the cool things about large language models is you can do instruction fine-tuning on them. So one thing that you could do is you could do instruction fine-tuning and say, when I ask you for, given a picture, I want you to come up with a funny caption. Here are some examples of pictures and their funny captions. You could train the model to do that if you wanted to. All you'd need to have is some training examples of images and funny captions to do training on it. If we didn't want to actually train all of the parameters, what could we do with stuff that you've already learned here in this AI summer? What's one way that you could train up a model without having to take on the expense of training the entire large language model? Yep. Gio, I'm sorry, Ezra, you had an idea? And Anant, I saw you too.
You could do both RAG and then you could fine tune.
Yeah, oh, so that RAG is interesting, right? So it could be, if you found, oh my gosh, this is an image of taxi cabs, we'll do RAG against, all information about taxi cabs. I like that. Plus, absolutely, you can do fine tuning. You can do parameter efficient fine tuning. Anant, you called it out. You said LoRa, right? Absolutely, those are both things that you can do. Anything that you can do to improve a large language model will improve this kind of an approach, this lava approach. So instruction fine-tuning, tool use. I love the idea of RAG. Haven't seen that done yet. Could absolutely do that. So anything that would improve the performance of a large language model will improve this. What are some other things that you might do to improve this model? So training, parameter efficient fine-tuning. What else could we do?
Could we add more efficient or more detailed metadata so that the model can then group the information in the vector space more accurately?
So that might sort of look like a little bit more training about images. What's interesting is, yeah, you probably could gather, you could take metadata from the image and maybe feed that in. I don't know if anybody has done this, but there's a ton of metadata that goes along for the ride with your images. Best example of this was at BuzzFeed. It wasn't BuzzFeed, it was Vice. A reporter with Vice, which isn't really around all that much anymore, visited a drug cartel leader in South America, took a picture, and it was supposed to be totally secret. Nobody knew where this person was, took a picture, and then uploaded it as part of a story. Well, guess what went along for the ride? The geotagged metadata. And guess what happened shortly after that picture was posted? Helicopters came in, and it just, yeah, it was He posted where he was. So metadata is a really interesting thing to actually include with images. Absolutely, you could do that. If the large language model can know it and reason about it, that could be useful. So you'd know that that picture, for example, was taken in New York City because that could be part of the metadata. Or anything that else that you can do to train models to understand images more. Other ideas. Let's see, we have a couple of text. Adjust hyperparameters like learning rate. Yes, you can do. And it turns out that hyperparameters are extremely important for this. And we're going to take the last few minutes of the session to talk a little bit about doing your own training of Lava 1.5. It turns out the hyperparameters are really important for that. One of the things, for example, we talked about how R, that lower dimensional representation in LoRa is usually like maybe 8, maybe 16. Not for this, 128. So you need a higher dimensional space, which kind of makes sense. You need a higher dimensional subspace to learn on because images are very rich. There's a lot of representation there, and it doesn't compact down as nicely as just text does. So that R has to be larger. Excellent. Semantics layer, yeah, so you could make that multi-layer perceptron. And just to remind you of what that looks like, as you're doing that projection from that projection right here. Nope, right here. Nope, right here. This projection, that could be heavier. These little orange things, those are your multi-layer perceptron. You can make that a bit bigger. So you might be able to make that bigger, more training, and so it might do a better job of projecting down to the space. But here's something else you can do. Just choose a better and better LLM, one that knows tool use, one that knows instruction fine-tuning, has been instruction fine-tuned. Absolutely, you can do that. Along the lines of what you all were talking about too, sort of that metadata, or the understanding about images, you could do reinforcement learning from human feedback on this. You could have it learn in that way. So it's not training materials. It could be artistic styles. It could be interpretations. Anything that can be learned by the LLM is fair game. So getting a better LLM, doing parameter efficient fine tuning, doing training, all the way, improving this learnable part right here. You could improve that. All of these are ways of improving the model. Let's see if there are other ideas. Yes, okay, the MLP layer, exactly. All right, so how good can you get? Well, turns out really pretty good. So one way to improve is, and this was just recently. This is January 10th. We're going to see one which is even just a few days ago. One thing is you can improve the input image resolution. And that's using that trick of having those two, doing the smaller and also the rescaled image so you can get both the finer grain, but not lose that overall view of that as well. So you can get more visual details and more aspect ratios. A better visual reasoning OCR, you do that through better visual instruction tuning data mixture. So this is changing what you're training on. And it turns out, unlike CLIP, which required hundreds of thousands, millions of examples, here you can do it with really a small number of very well curated examples. You could have better world knowledge and logical reasoning by getting a better LLM, one that's could be larger or just trained on much more data. Remember, the very performant models are not necessarily bigger right now, but they're trained on many, many, many more tokens. But you can take those off the rack and then use those. And then finally, you could do better deployment as well. So something else which is interesting here, in the next update, which was from May 10th, so even after we started this AI summer, they expanded Lava Next even more with stronger LLMs, because between the time we started this and now, some really good models, Quinn, Llama 3, all of these are available now that were not available before, and these perform much, much better. So think about an embedding, because remember, you've got to get that embedding down into it. Now, instead of Vicuna, now you have much richer models so that embedding works better. The other thing is that now you have video understanding. It turns out that even though it's not as powerful as, say Gemini 1.5, it turns out you can do a lot just from taking multiple images of what's happening, and the model understands really quite well what's happening in videos, even though it's doing that type of encoding in a very different kind of way. So it has strong video understanding capability, even though they haven't changed anything architecturally about this. All right, so how well can it do? Let's see if I can. Let's see, where are they? So here's an example of so it's the video, and what you're doing is you're grabbing just frames out of the video, and it does a really nice job of what's happening. The video may have been manipulated, or it's composite of two different scenes to create an illusion. All of this just because that large language model is so rich and is able to uncover useful information. So let's see now, where did I put my performance metrics here? So here, let's see, here's GPT-4. Here's the results with language multimodal LLMs eval. This is GPT-4. This is this is state of the art right now. So Lava, which is trained on, this is even the large model was trained on really just a handful of DGXs, Lava is beating GPT-4V on many of the benchmarks. Not all, but on many of the benchmarks. So here, it is outperforming on a few, and a few of them it's on this one it's much better, but Lava is far above any of the others that are open source. So here you have something which is trained on far less data and is yet highly competitive, and as you saw here, can even do things like dealing with understanding video. All right, let me pause here. What questions or observations do you have about Lava? What about contrastive learning, augmented views of the same data to an enhanced model? So Michelle, I think you're right. This may actually be more along the lines of generating useful training for this rather than contrastive learning, as we were talking about at the very beginning. Because remember, with contrastive learning, very little is happening. All it says is this text goes with this image, therefore the representation should be close. This text does not go with this image, therefore the representation should be far away. So really not very fine grained at all, right? And so if you want to get useful representations out of it, you have to train on an immense amount of information. So this representational space organizes in a way that's useful to you. So huge amounts of training. What you're suggesting here, though, probably useful, and as a matter of fact, is useful, which is you can use these large language models to generate useful data for the training. And yes, it's useful to actually give good examples and bad examples. Let's see what else we have here. Okay, great. Other questions and observations? So yes, so Lava can do very complex tasks, and you can up its power by using a better and better large language model, or by doing training of that large language model on tasks. It also is capable of what's called zero-shot or in-context learning, zero-shot tasks or in-context learning, where you get to just ask about the image. You've never trained on it. You ask it things like, what's unusual? What could this mean? All of those things you can ask with zero shot, or you can do in context learning as well. So I'd like to hear if you are able to do additional training, like give it images and text and actually do additional training, what are some things that you might like to train your own personalized version of Lava to do? Does anyone have visual tasks that they're having to work with? Analyze my patient condition. Oh, I love that. Yep. So you can imagine taking a scan. A scan. So if you have a medical scan and you have a really good write-up about it, you now have a way of richly representing the scan, which is an image, or maybe in a video, and a description of it. So for example, let's say that you were doing an echocardiogram of ejection fraction of a heart. If you have a large language model which is very knowledgeable about ejection fraction, cardiac function, and you also had a good embedding, how far could you go with just some additional training to have it actually directly interpret those scans? fMRI images could very well be, especially now that you have this Lava Plus approach, which keeps both the large and also can do the finer grain as well. Again, helpful remember, for the language model, you're going to want to have something which is extremely knowledgeable about whatever you're doing fMRI of, right? But the more description there is, the better those projections are going to work. Here's the cool thing. You do not need to be Google to train this, especially with parameter efficient fine-tuning methods and with a decent amount of compute. You can actually train models to do this kind of work now. This was not possible just even 4 months ago. And now, far more possible with the release just from May 10th of the additional capabilities proven out of working with the video. All right, how do you do the training? Let's talk about training. We'll finish up today talking about training. Before I jump into the training, I forgot to mention at the very beginning, we are going to have an AI showcase. So I mentioned this now because if this me talking about the training and showing you where you can actually learn more material on the training, if this sparks an interest in training a specialized model, you would have an opportunity on August 23rd, which is after the classes begin here, to present your work in an AI showcase. You could be invited to join us for AI showcase. It's going to be for all the work happening in AI on campus over the summer. It's going to be a nice event. It's going to be catered, be a nice opportunity for you to present work that you've done, you with a team, or you with your lab. So keep that in mind. If this sparks something and you want to spend the rest of the summer doing some of this, we'd love to have you for the showcase. To that end, we're going to start offering free consults on Fridays. Sharo, was this 10 to 12? Is that what we were doing? 10 to 12. We'll send an email about this. We'll have a virtual version and an in-person version. And this is our AI Fridays. You can drop in as you begin working on some of this stuff. You want to actually start, having some help. Drop on by or drop on in using Zoom. We'd love to help you talk through how to actually carry this work out. So questions about AI Summer Showcase or our AI Fridays coming up. Oh, and if you're in person, we're also going to have a mixer immediately following we're going to have our drop-ins, then we're going to have demos, and then we're going to have a mixer after that on Fridays, because it is summer. Any questions about those? All right. Let's talk about training. The training that's talked about in this really very nice weights and biases write-up is a little bit older. You notice that this is February 9th, 2024. it's still going to hold because a lot of the things that we were talking about was really, remember, we get to go back and so long as we have a way of training up this or the model itself, this should work. So a lot of this is still going to hold. And the link for this is in the repo. So it's under the Wednesday sessions for repo. So here's what the training data looks like. You have an image, you have a caption for the image, and you might have multiple captions, right? So here's one, a group of people standing outside a black vehicle with various luggage, okay? So you could do that text and then that image. You get luggage surrounds a vehicle in an underground parking area, okay? People try to fit all their luggage in an SUV. So these are multiple training examples. You take that same image, but you train it with multiple captions. So interesting sort of cheap thing that they did in the original Lava paper was they gave just the first text description that they had generated by a person and had GPT-4 at the time generate new versions of it. So just rewordings of it, and they used that for the training. It worked out really well. So you could either have multiple human generated, or there are tricks that you can use to generate more, and use them all as different training examples. So this is right here, 1, 2, 3, 4, 5 different training examples, all using the same image. You can also use context. So here we have actual bounding boxes. So you can, this is the idea of metadata. So this is additional context type 2. So this could be multiple types. So for the training, you can do the following. What type of vehicle is featured in the image? Answer, image features a black sport utility vehicle, right? Or you could ask for a detailed description or complex reasoning. These are all things that you can train the Lava model on, and that training is, again, occurring in a couple of different places. One is it's training up this multi-layer perceptron, but it's also can be training up the large language model itself. Those are the two main areas of training. Okay, so a couple of questions here. Curious to see how Lava compared to the AWS Bedrock we experienced when it seemed like Lava is smarter. Yeah, no kidding. Now, you could do this in AWS Bedrock. So you can remember in Bedrock, we didn't talk about it too much, but you can do training within Bedrock, but you're going to need some decent compute for this. So this is going to be like DGX level. If you're interested in training up, we have compute grants. And there are also ways to actually split this up, and so you can do it on less hardware. We're going to be talking about that in a moment. And Esra.
So we've discussed how LLMs aren't great with mathematics.
Yes.
If I put up an image of an architectural site plan and I say, hey, what's the proximity to, let's say, the lot line? Do you think it can accurately compute where there's a scale on the plans so it can identify that and say, yes, it's approximately 30 feet from the lot line?
This is where that choice of that LLM gets really important, right? I mean, how much, quite literally, how much does it know about these drawings? Has it been trained on architecture, on design? If it's never seen any of that, then it's not going to be able to do too well. But if it's been trained on text around drafting, for example, then it might be able to do a lot better. Because remember, it has a lot of brute force. So it can do it, but it's not going to be just out of the box. It's not going to be great with numbers. But if the numbers are recurring, and if it's occurred in the training corpus, or if you can do additional training on it, then it might be able to do well. This is one of those things where you've got to try it to see how well it can do.
Thanks.
What if you could label sections in an uploaded image to provide context in a chat model? Yeah, so I wouldn't be surprised if we're going to see a lot of annotation built in, to sort of do this more efficiently. But there is context type 2, this, the bounding boxes, information, measurements, things along those lines. All right, let's talk a little bit more. Here's the architecture that we've seen. This is just a little bit different. We have the image, the vision encoder, and this could be lots of different encoders. We've seen lots of different encoders. The projection going directly into the language model. And here we have a language going into the language model. So data can come from different places. In this tutorial, it comes from the OK VQA dataset, but you can actually use your own. And what it needs to be is it needs to be in an affordable and a suitable format, but there's actually a script that will help you be able to do this. The datasets library in Hugging Face will allow you to do this, so you can use this directly. Here's code. Here's the script actually, which can take images and captions and package them up appropriately for training in Lava. This is the Lava JSON that it needs. You can see, it needs this labeling, from human, question, formatted answers. So this is the format that it needs. The training, you can start with this particular starts on the original Lava repo. So they actually have a lot of the code in the Lava repo. I don't know if I linked to it directly in our repo, but I'll put that in. But it's in the project repository, so it's right here. So you can actually directly from Hugging Face just load up that Lava 1.5, and actually the Lava 1.6 and the other ones are up there now too. So you might be able to do this training even on the 1.6 or later versions. I haven't tried it, so I'm not too sure. And you get to use LoRa. In this case, you might want to use QLoRa, which is the quantized version of LoRa. This is where those parameters come in to be very, very important. So the hyperparameter is going to be important. They make use of the 4-bit normal float. I don't think we talked about this, but QLoRa also introduces a new data type, which is a 4-bit float, but that's designed to work with normal data. So 0 and then off of that. And even though it's just 4 bits, it turns out to be enough granularity there to actually give you useful training. Something else which is important that we've not talked about is deep speed from Microsoft. They have something called Zero technology. The cool thing about this is it splits up the part that QLoRa can't touch. LoRa specifically is dealing with, you might remember, it creates a low rank a version of the weights in that feed-forward network, and so you get to train just those. But remember, I said, but it's still big to train because the optimizer takes space, Atom takes space. Those you still have to calculate the gradient across all the parameters for the model. Well, Zero actually allows you to split that up in different ways. The problem is that without doing something like Zero technology in deep speed, it all has to fit into memory. Everything needs to fit into memory. So the gradient, momentum, the various numbers that Atom likes to keep track of for this back propagation all needs to be in memory. Even though you're only training like 1% of your parameters, you still have to put everything in memory to calculate all of the gradients so you can actually do the back propagation. Zero allows you to split it up in various ways, and so you can fit a much larger model in a much smaller compute space. So you can actually do this on off the shelf. You can probably do some of this quite possibly if you have a beefy Mac with an M3 or an M1, M2, and 3, or on some of our compute, and we can make compute as well. One interesting thing, this is called stage 3. It offloads the gradients to CPU, which means you get to use all the memory of the machine. It's slower, but it means you can actually train it. So the train command here actually handles a lot of what you need to do. So this is actually a really good starting point for your work. Yes, you're going to have to work with these parameters, but know that your friend in figuring out the training is the large language models, the AI models, to help you figure out and to fiddle around with these to get these to work. These are the key parameters. I mentioned LoRa R. So normally it's like 8 to 64. Here you've got to choose something much larger, 128. So that's going to be big. And these other parameters too, but you can actually go through and choosing and experimenting with these to see if you can get it to start training. But then once you do that, now you're going to be training much like you would train any other model. So the fact that you're doing this trick where you're training essentially this model plus a few other things allows you to treat this like any old regular training. That would be very difficult, if not impossible, if you're using a huge model like this, or if you're doing a model like this, which has multiple models. The training is vastly simplified because it essentially is the training of a large language model or parameter efficient fine-tuning of those models. All right. Now, and you can do inference on this as well. This is actually the code to do inference. So really, in a fairly short write-up in weights and biases, so long as you have data, appropriate data that is going to look a little bit like this, then you have a script here for you actually to package up that data, and then you have the training script right here. So really all you need, if you have your data, and if you've worked with it, is you need the compute to be able to do this. And again, it's not huge compute. So to me, this is pretty mind-blowing. The thought that I could actually train on my own for myself, my own specialized multimodal model, which, by the way, performs, performs not too differently from GPT-4V, is really, really exciting. So let me pause here. We've done a quick overview of what the training might look like. Ezra, you had a question?
Sorry, I didn't lower my hand from last time.
That's not a problem. So questions and observations about training your own multimodal model. Shane.
Do we have any idea how this might compare to 4.0?
It's, that's a really good question because 4.0 had not been out. I'm waiting for that. I think it's going to be a matter of days, really, before we see the comparison with GPT-4V. GPT-4V wasn't bad at all. I mean, we saw, was able to do my quantum chemistry, right? So it's not bad. But it does seem like the training for O is very different. So if you think about it, my best guess is that GPT-4V was looking more like this, right? Or maybe something like Flamingo, because you had this very heavy-duty GPT-4, and so it was combining it, but it seemed as if it didn't have access to all the information about the image, which meant that it was not being trained in here. I would not be surprised at all, if GPT-4o took something that was more along the lines of this kind of an approach, where it's projecting into maybe the self-same space, because GPT-4o, even it's called GPT-4, is a from scratch training of a model, because it used different encodings, tokenization scheme. And remember, you can't change your tokenization scheme once you've gotten started. GPT-4o used an entirely different tokenization scheme. It is a different model from the ground up than GPT-4. Other questions?
Yeah, so Jesse, if we wanted to play around with this, I know you were going through where you could fine tune it, or what would be the easy, let's just say, can you do this on Google Colab with a GPU, or is it you need more than that? Like I'm trying, I don't know if I have enough horsepower on my own computer.
No, fair enough. One thing is keep in mind, it really depends on which model you're choosing here, right? So what's your language model, and also what's your embedding model? If you use something which is huge, if you don't use CLIP, instead you use something which is bigger, and let's say you use Llama, it's not out quite yet, but should be out soon. Llama 400 billion parameter. You're going to need something much bigger than Google Colab. But what if you chose a small model? I mean, there's been some evidence. I've seen a multimodal phi model, which is like less than 2 billion parameters. Yeah, you could probably train that on Google Colab. You just have to make sure that the infrastructure is good. And if there's not already a checkpoint, because one of the nice things about Lava is it has a bunch of checkpoints for different backends. If you don't have that, then you do have to train it from scratch. And if you're training it from scratch, then you're probably going to have to commit to like a day's worth of compute on whatever hardware you're on. But that might be about it, depending if you have a really small large language model that you're going to be training. So it's possible.
Yeah, I'm looking at some of the ones that are Hugging Face. They're probably pretty user plug and play, I would think.
But think smaller models and think deep speed, and especially that trick, that zero of like splitting up the compute. If you're doing that, it's helpful to have multiple GPUs if you can get them. So that sort of rules out Colab.
Okay.
All right, other questions? Yes, shoot.
Okay, I also have a question for fine-tuning the model. Suppose, say I want to train a small model on Google Colab, and I pay the GPU on Colab. So is there any way that I can estimate the running time of my tuning? Because I don't want to quickly run out of my quota. So yeah.
Yeah. So the first thing that you do, of course, is and if you're doing the page, remember you can get an A100. You might be able to get an A100 with 80 gigabyte, which might be able to support some of the smallest of the models. Just have to try it and see. And really, that's an empirical question. If you have really tricky training data that's hard for it to learn, it'll take longer. If you're simply trying to get it to do a new kind of a task with existing data that's already learned, that could be faster. If you're going to be doing QLoRa, it certainly could be faster. So it's all depending on which of the things you're doing. You're doing QLoRa and you're doing deep speed, and the problem that you're trying to solve is more easily solved. You might be able to get to a good performance level quickly, but it really depends on all those things.
Okay, got it.
All right, folks. Here's my charge to you. Start thinking about how you might want to apply everything that you've learned so far. We'll be finishing up on Friday. On Friday, we're going to be talking more about Llama and Phi. We're going to look at Lava, actually trying it out. We're going to be looking at long context models and coding with long context models. So we're going to be talking about that and sort of closing things out on Friday. But think about what you might want to build. Think about what problems you might want to solve. I'm hoping that that today's session in particular sparks some ideas. Now that you realize you have so much power at your beck and call, all you have to do is think about how you want to solve a problem. And keep in mind that what we've done so far has been image and text. It's possible you could go outside of image, right? Might require significant more compute, but image is not the only modality. Just like they were able to jump up to video, just doing with like multiple images, think about what you might be able to do as well. Think about what other types of modalities a large language model representational space might be able to directly support. I'm going to love hearing your ideas. All right. Don't forget, we have AI Showcase coming up August 23rd, so start thinking about what you might want to do for it. We're going to start next week our AI Fridays, 10 to 12, both in person and virtually. And if you're in town, we'd love to have you drop by. All right. See you all on Friday for our last session. Stick around if you'd like to ask questions during our office hours. And thank you, Sim. Yeah, absolutely. I'm completely stoked myself. There are a number of things that that we're going to be trying out over this coming year. Thank you.
Hi.
Hi.
Question.
Yes.
So I guess you guys already know I'm into the healthcare part, and we are trying to figure out things how we can make it work. Unfortunately, I have not found a lot of stakeholders to help me with the support in the healthcare. So I got the permission to use the data set. I just need to clean it up to
Yeah.
get rid of the name and all this credit card name and all the stuff and really nail it down to the healthcare. So that one may be take me some time to clean
Sure.
that one up. But I
Yeah.
want to play. Is that I want to find a playground. I don't think my MacBook can support it. I'm not sure how my MacBook can support this. I want to start with a playground to just one of the ladies from she is from the VUS and she sent me the Azure training that say how I can play with pressure injury and let upload the pictures to the system to let the system learn. I
Was
was
this
like,
a nurse practitioner?
she's not. She works in the IT for the VUS and school of nursing. So I have not played with that,
Do
but I
you know
was
her
just
name? Because we might be writing a paper with her. If it's who I'm thinking about.
I think her name is Lily. Wait a second. What is her name?
Okay,
Give me
okay,
a
no,
sec.
this is someone else. So there, yeah, there
Yeah.
is actually someone that we worked with on staging of pressure sores. Um,
Her last
a
name is
lot of
Sadoun, Saadoun. I don't think she's
someone new
working
that's
with.
great. Yeah.
Yeah.
So, which is immensely useful. And there's a lot of text written on that. So
Mhm.
and the nice thing is that is very close up. And if it's all patient information is removed, then you might be able to do it. But what I would suggest with that is first, don't wait for the data. Have some generated stuff, even like make stuff up, right? And if you can get it to run, then that means you can train on it,
Mhm.
right? So, and then if it's like it never works, it's like, okay, well, maybe don't go after that data, go after something else, but start with mocked up data and see if you can get it to learn on mocked up data. That means you have the entire pipeline ready to go.
Because right now, if I'm saying, let's just say, play with the playground is with the image. I need the image decoder. It looks like Lava is getting very smart to
Yes.
recognize the pictures and all the stuff.
Lava out of the box might be able to do a fair amount because they built Lava Next on top of Lava 1.5, right? So they're just building on top, and that's what we should do as well.
Okay.
Yeah, but absolutely, just and if you don't have data that you can do that, ask Stable Diffusion or one of the other models to generate, a stage 1 pressure sore,
Sim, when you're ready for connection to stakeholders, I can help you with that. So I'm a faculty member in the Department of Biomedical Informatics, and know all of the folks that are leading the advanced group over there and interested in doing all this kind of stuff. So, so just reach out to me.
Thank you.
Fantastic. Other questions or comments? And yeah, Shane, and my mind is going to all the different images that that we have in and around the medical record and thinking about, especially if you have a model which is a tool which knows tool use. I mean,
there's so much. I know that VMC is trying to really put the right framework in place to do this well and to to study it well. So of course we have to be careful, but we have our own instance, and VMC does have we're able to use the VMC instance and include PHI, so that's helpful. So we can do those projects there.
Yeah.
I'm actually meeting with a group next week. Some clinicians reached out to from the Department of Medicine, reached out to the School of Medicine leaders, and someone was at a conference, heard Eric Topol speaking, who's a physician leader in this space, and he mentioned the possibility for assessments in the future of students. And a real-time video or audio of patient encounters. And so, we're meeting to understand what it is, what's the problem we're trying to solve there. I'm kind of thinking that a place to start might be a place where we have students interacting in an environment with standardized patients, or actors, but we already have video and audio of those encounters, and it might be a good place to get data and train a model on that to try to pull out concepts. I don't know. Does that sound like a right approach?
I think so, and especially with I would not be surprised if we I'm very curious about getting audio in there, right? Because right now Lava, for example, does video, but video without sound. But I mean, we already have very good audio models. What gives me hope is that we don't have to be Google to get really good performance on these models now. So as the large language models get more performant, then they're just going to be better and better spaces into which to project all of this. Right. So some of this is brand new, like audio being projected in that, brand new. I haven't seen it yet. Video, that was May 10th, right? Right. So we don't have to have like Sora or something along those lines, which is huge. We can do it, which is much smaller, which means we ourselves might be able to do it in a secure fashion. And we get to experiment. If it's small and cheaper, then we get to experiment and explore versus we need to write a grant. We have to wait for the money to come before we can actually afford to try it.
Yeah. I guess my other question for you is around that is, I was excited when we talked about, calling functions and getting discrete data back and stuff. And it's really powerful. So one of the things that we need to do in healthcare and in medical education is be able to standardize our reporting and around things, right? And billing, everything is tied to standardized terminologies. And so I've been thinking about ways that we could use an LLM to take some input, analyze it, extract something, and then call the UMLS service, Unified Medical Language Service, and get back concepts to sort of codify, and then return that, so we can report on, identify key learning points, required clinical experiences. I don't know. So now, have you seen people do?
How many pages would you say UMLS? The documentation for UMLS is a couple of thousand.
I mean, it contains. So UMLS is a meta thesaurus, so it millions of different concepts that are all interrelated. But I don't know about the documentation. I mean, sure, it's 1,000.
Yeah, I mean, So so tool use, absolutely. Where you call it with descriptions. So it's a couple of things. One, we're able to start getting long context models now, even with like Llama. So Llama has been extended to like 1 million tokens. So you can think about now we can project down into it, and we have this very long context window. And one of the interesting things you can do with the long context windows is you can put documentation directly in there if you want to. But UMLS you can almost think of it like a super RAG, right?
Right.
And so it's pulling in. So either it pulls in and does the tagging, or it pulls in useful things into that context. I think there's a lot of runway to do useful things like that. It's a really nice combination of being able to get so much into context and it being a tool used to either pull back answers or additional context to then work against. But I'm really curious about how well a model could do, around reasoning.
Yeah.
Yeah.
Because I mean, right now, so there's a tool that I'm leveraging for a project. So we have this innovation grant with the AMA to around precision education in medicine, and so we identify that a student wrote a note on a patient. They're learning about the patient, and so we're looking for they have 100 required clinical experiences that they have to have in medical school. So there's an existing tool it's called Word Cloud that Dario Gize at the medical center created, but it's very, it's old school, NLM, right? It's just looking for specific, or NLP, sorry, it's just looking for specific UMLS concepts, certain CUIs. And so we started the project a year ago or a year and a half ago, and we're like, okay, we need to build out this essentially data dictionary of of these CUIs to find these required clinical experiences. But I'm like, if I were to do this now or start this now, I would use a large language model to find the concept.
Oh, absolutely. And then, there's some really nice work on graphs, knowledge graphs from text. So we were having a conversation with a group of students that is spinning up a company. Chat EDU, is that HRO? Is that what they were? Yeah, Chat EDU. But the idea there is, I could certainly see, what is incomplete or what is the shortest path or what is missing, and graphs are great for that. And so tool user where it's able, maybe another tool to actually create the graphs, but then make the model a user of that graph.
Cool.
Yeah. Excellent. Other questions, discussions?
I actually don't, it's not more discussion, it's not the idea. So I'm pretty sure some of you guys already aware that when the provider can chart using their audio, like they just say the word and then they can chart in the system. So one of the things for the nursing workflow is we have to chart a lot. I'm wondering, do you guys aware of anybody is working on a project? It's like, let's say I'm inside the patient room right now. I can just say, hey, Avatar, turn on the charting system right now. The patient SpO2 is 90%. The blood pressure is 200 over 100. So it can detect my information and then send the prompt. And this is the prompt. I need you to chart this information into whatever system that is located. I know right now all this large language model is only trained on text and also pictures, but not so far in the audio part. But is there any company is trying to work on that yet? I think this would be fascinating and reduce a lot of time.
I could take that one, Jesse. If you I don't know, you may know more than me, but yes. So Epic, the electronic health record company that Vanderbilt uses, has a partnership with Microsoft, which obviously is using ChatGPT. So they already had a voice assistant. Microsoft also owns Nuance, which was, before they formed the partnership, was the leader in sort of voice recognition or software in healthcare. So they have great voice recognition technology available. Right now, it's mainly been cost. So I think the cost has come down and the training time has come down for the providers. They have a product called DAX, called the Dragon Ambient Experience, where the provider just talks to the patient and sort of narrates what they're doing, and that generates documentation at the end of the encounter. So I think it's getting there. I can also put you in touch with my colleague, Yakumu Crystal, who's been—
I was going to mention Ya.
Yeah, the leader in sort of voice interaction with the electronic health record. She was working on a project prior to all of the large language model stuff with Nuance and Vanderbilt, creating a product called Viva, and she works with Epic to try to advise them on these things. So happy to connect the two of you.
That would be awesome. I know we need nurses to be in part of the stakeholders There's too much charting. We try to minimize that.
Yeah,
And if you haven't met Patty Singstack, you should meet
Yeah,
Patty.
that's my
Yes.
advisor.
Oh, got it. All right.
And the other thing which we've not seen a lot yet, but we're certainly going to undoubtedly see is going to be including the image and the video. Because this is such a lightweight way of doing it. You can imagine, and this is kind of like we've been talking about this for years of like where where you might have cameras. Well, now because inferencing is so light, it doesn't have to leave the room. So you literally could be looking at something. Let's say you're staging a pressure sore, right? You could be looking and say, well, it looks to be, and then right now the technology is there if you have the camera in the right place where it could actually absolutely make sense between what you were saying and what the image is and correctly represent what's going on there. It's very exciting. Other questions, comments, or it does not have to be healthcare.
Yeah, so I just posted my question
Okay, good.
in the chat.
Yeah, well, so this is okay. Regulatory policy. That's where I'm thinking. I love and Nestor, you were the one who brought up RAG, weren't you?
Mm-hmm.
I love that idea. So using RAG along with the image, I think that could have real legs, and that's a way to handle that rapidly changing. So imagine that you have a model which has a decent context length. You're able to get the image in there, and then you do RAG once you discover, oh, that in the image it said, Nashville 2020, or and have it pull up, appropriate, documentation based on that. I think that really is a very interesting idea. I think training on changing data is hard, right? So you want to train on the tasks and to make sure it has a rich enough representation in the LLM itself. So choosing an LLM well, making sure that there's a rich representation. DSI team, or everyone here actually, we talked last Friday about tuning by proxy. There'd be nothing keeping you from, say, taking a llama 8 billion parameter model and then using the output of that's already been augmented with the image, and then using that to steer in a 400 billion parameter model, so it has all that world knowledge. Discussion, but yeah, we're gonna have to try that out. So I think that using that long context wisely, and I think one of the ways is doing RAG and pulling in the appropriate data. And it could be a specialized RAG, right? It's not going to be just like, oh, it's like RAG, it's just for free. You might have one that actually is backed by a database or by, metadata. And so if it is, do you do civil engineering, or what sort of, I want to give a good example.
We do environmental and urban planning. So we're taking, in certain cases, let's say we're supporting a client doing a public works project. We're taking architectural and engineering plans and doing assessments, identifying how the project will impact the environment and the community. And
this much impermeable that you're going to be putting over here, what are the regulations here for storm flow? Back when I was in high school, I did I worked on a proto spreadsheet. This is how old I am. So this is before spreadsheets. But we did something very, very similar to that with civil engineering firm looking at 100-year storms and yeah.
Like FEMA maps and whatnot.
Exactly, that's right.
Yeah.
But you can see that absolutely pulling that into context. And so it can then take the image and reason against it well.
Well, I'd like to create a model where rather than in an analog form having to, let's say, go to the FEMA map, we can integrate the general plans and already integrate those FEMA maps to identify the ideal areas for development and also eliminate the areas that have the highest environmental risks and especially in the context of climate resilience. Being able to quickly have a tool for environmental and urban planners that they can reference, but it's going to incorporate also these like GIS maps. And that's where I'm a little stuck, I guess you would say, because a lot of this stuff is in interactive maps and I need to learn more to see how I can integrate that data.
Do you want to do a semantic search across maps or within a map? Show me the areas of highest impact.
Yeah, well, all the above, like areas that are, let's say they're pristine riparian areas, we want to preserve those. Identifying different types of habitat. Let's say there's a state or federally protected species. We want to avoid those areas.
Well, I mean, we kind of saw an example of that with the tool use, right? Where it was doing semantic segmentation. So, I mean, so a couple of things are coming to my head. First of all, tool use to do semantic segmentation, but then training the model to be able to do that type of segmentation or identification. That's almost you'd want to do that